We're back for our last video in Chapter 9. This is Section 9.3, number 86. We hear that listening to Mozart improves students' performance on tests. Maybe pleasant odors have a similar effect. To test this idea, 21 subjects worked two different but roughly equivalent paper and pencil mazes while wearing a mask. The mask was either unscented or carried a floral scent. Each subject used both masks in a random order. A table of data is given in the book with the subject's times and seconds with both masks. Note that smaller times are better. Do these data provide convincing evidence that the floral scent improved performance on average? So because we're checking to see, let me go backwards first. There's 21 subjects that work two different but roughly equivalent mazes while wearing a mask. So that means that they each wore each mask, meaning we have a matched pairs design. Because we have a matched pairs design, it really becomes just one variable, where your variable of interest is going to be mu of d, where that stands for the true mean difference. And I'm going to calculate that by doing the scented minus the unscented. And time it takes to complete the mazes with the mask on. Now pay careful attention to that, because we have a matched pairs design. It really is just one variable, which means that we can still do a t-test, a one sample t-test. Now right now you only know one way of doing a t-test, but as soon as we move into the next chapter, you're going to have instead a two sample t-test. So you have to be able to recognize that this is a matched pair design, which means you only have one sample happening. Although you're going to take it two different times, the one thing that you're looking at is the difference. You're not looking at them separately. So it's going to be huge come later chapters. So our null hypothesis is going to be that that difference is actually equal to 0, meaning they have the same effect. Whether you have a scented mask or an unscented mask, they're both not affecting the speed at which you do the maze. And our alternative hypothesis would be that we want to see if they can actually improve performance, which would mean they can do it faster with the scented mask. So that means we would be checking to see if, that should be a less than 0. All right, sorry for the long pause. I just realized that I needed to show you where the data is coming from before I start jumping around and taking care of all that stuff. So I'm in your book on page 598, looking at number 86. The data is given here to you. You have, for each subject, there's the unscented data and there's the scented data. So what we're going to do is we're going to take their difference. Remember we said scented minus unscented, and that difference is going to become our new data values. So I'm going to pause for a second and come back to you with this setup in my calculator. Okay, so to check my conditions, I'm going to go to the random assignment first. We know that there was a random order in which they were assigned the mask. So that is the randomness that we need in order to be able to infer this upon a larger population and to use this sample as our unbiased estimator. The other thing that we need is our actual data. We need to be able to look at that data and see what the distribution looks like. So I put, just like it was in the book, I put the unscented here in L1 and I put the scented here in L2. Now because we defined our variable as scented minus unscented, I'm going to define L3. Notice I'm up here in the L3 box. I'm going to define that as L2 minus L1. And when I do it while I'm up here in the L3 box, I can then just hit enter, and it's going to autofill that full thing. So now I have all of my data there in L3. That's the data I'm going to look at the graph for. So again, I'm going to look at a scatter plot first because that usually gives me the best picture of distribution. And I'm going to do zoom 9 on that. Okay, so that leaves me kind of questioning. Now remember, we had a sample size. We had an N of 21. which is a pretty good size. So I just need to check to see, is this an outlier over here? Is this really strongly skewed? What's happening with that? So my calculator just set this window. I'm going to check again a second thing. I'm going to check with the box plot as well. And I'm going to zoom 9 that one as well. Now I see there's no outliers, but this might have me questioning a strong skewness happening there. So again, I'm going to do one more thing. I'm going to check one of our stats. Oh, you know what? That's what's wrong. I was doing all of that with L1. Remember, I don't want to use L1. I need to be using L3 because that's where my actual data is. So try not to make mistakes like I just did. L3 is our data. Whoops. Zoom 9. Zoom 9. That looks much better. Okay, so this histogram is definitely something I can use. So I would make a rough sketch of that, outline the rest of my conditions here. Now we have that all written up. Notice my histogram is not the greatest histogram. This is just part of my work. If I was asked specifically just to make a graph, like in part B, if it just asked you to check the conditions and graph your sample data, then you would make this as perfect as possible. Because I'm just using this as part of my problem and checking my conditions, I'm just gonna have a rough sketch there. So after I do that, I can go to my technology. And again, we're gonna remember this time that's an L3. I'm going to press Stat, go over to Tests. I'm doing a t-test. I have data again. My null hypothesis was that it's equal to 0. I have to remember it's an L3. I am doing a less than for my alternative, and I'm going to calculate. And all of this is going to go into my answer. So we have t is equal to negative 0.349. P is equal to 0.3652. We have degrees of freedom equal to 20. There was an x bar of negative 0.9567, a standard deviation for our sample of 12.548. And to make that conclusion, I know that 0.3652 is greater than 0.05, so again I'm going to fail to reject. So our conclusion is we do not have statistically significant evidence that the fluorescent improved performance. That concludes Chapter 9. Now remember to try to pair what we learned in Chapter 9 with Chapter 8, so you know when to use a confidence interval versus using a test of significance.